In this video, we will discuss capacitors in series and parallel. In particular, we will analyze circuits in which capacitors are connected in series and parallel combinations. We will show how to calculate equivalent capacitance for a circuit with capacitors in series and parallel combinations. And finally, we will solve few problems to highlight these concepts. Let's begin with a symbol for a capacitor in a circuit. Symbolically, we can represent a capacitor with two parallel lines, like that. So this represents a capacitor in a circuit. Another important component in a circuit is the battery. And this is how we usually represent a battery in a circuit. It is represented also by two lines, but one line is shorter than the other. So the longer line is the positive terminal, and the shorter line is the negative terminal. And we usually write the voltage of this battery like that, V. V could be 10 volts, 20 volts, and so on and so forth. Now let's represent capacitors in series. Let's assume we have three capacitors, C1, C2, and C3. So how do we connect them in series? Series connection of capacitors are as follows. They will appear side by side to each other, like that. So let's assume the first one is capacitor C1, the second one is capacitor C2, and the third one is capacitor C3. And they can be connected in a circuit to a battery, like that. So this is a positive terminal and it's a negative terminal of the battery. And this battery will charge these capacitors. So this is how capacitors are represented in series connection. Now what about capacitors in parallel combinations? So we have three capacitors, C1, C2, and C3. And this is how we connect them in parallel combinations. So the first one, the second one, and the third one, like that. Let's call the first one C1, the second one C2, and the third one C3. And we can even connect a battery to these connections, like that. So this is a positive terminal and negative terminal of the battery. So this is how parallel combinations of capacitors look like in a circuit. Let's look at the following parallel combinations of three capacitors as shown in this diagram. There are two important properties that we need to understand regarding such a circuit. Now let's assume each capacitor carries a particular amount of charges. Capacitor C1 has charge Q1 coulomb, C2 carries or contains a total charge of Q2 coulomb, and C3 carries a total charge of Q3 coulomb. Property number one that we need to know about capacitors in parallel is that the total charge of this network, meaning network in which capacitors are connected in parallel, let's say Q, is just the sum of individual charges, Q1, Q2, and Q3 in this case. So if you have three capacitors, C1, C2, C3, each carrying charge Q1, Q2, Q3 separately, the total charge in this circuit is quite simply Q1 plus Q2 plus Q3. Property 2. The potential difference across capacitors connected in parallel in such a manner must be the same. So that means the potential difference across capacitor C1 must be V, the potential difference across capacitor C2 is V, and the potential difference across capacitor C3 is also V, which is the same as the voltage provided by the battery. Now we are ready to calculate equivalent capacitance of this circuit. What is an equivalent capacitance? Now let's assume that we have a single capacitor. Let's call this capacitance of this capacitor CEQ. And this capacitor carries the same amount of charge as this network when it's connected to a battery with the same voltage, namely V. So the charge on this CEQ capacitor is quite simply Q1 plus Q2 plus Q3, the same amount of charge as in this network. So these two circuits are equivalent to each other, and the capacitance of this capacitor is what is known as the equivalent capacitance of this circuit. So our task is to calculate the equivalent capacitance in terms of C1, C2, and C3. Now we note that for the equivalent circuit, Q is CEQ times V, the normal equation that defines the capacitance of a capacitor. Since the first property that we discussed earlier, that says the total charge of this circuit is the same as a linear combination of all the charges of the individual capacitors, like that, and Q1 is quite simply C1V, Q2 is C2V, and Q3 is C3V, by also using the second property for capacitors in parallel, and comparing this to that, we immediately find the equivalent capacitance of three capacitors in parallel is quite simply the linear sum of the individual capacitances. Thus, generally, if you have n capacitors in parallel, as shown, the equivalent capacitance for such a circuit is quite simply C1 plus C2 plus C3 all the way up to Cn. Now let's look at the series combination of three capacitors, C1, C2, C3. The right-hand side plate of C3 is negatively charged, so the left-hand side plate of C3 is positively charged, and the reason is because the right-hand side plate of C3 is connected to the negative terminal of the battery. So C3 would have negative Q and positive Q respectively on its plates. The right-hand side of capacitor C2 would have negative Q on it because it is closest to the positive plate of C3, and the left-hand side plate of C2 would have the opposite, plus Q. Likewise, C1 would have minus Q there and positive Q there. So property 1 of series combination is that charges on capacitors connected in series are equal. That's property 1. Property 2 is regarding the potential difference. Let's assume that the potential difference across capacitor C1 is V1, across C2 is V2, and across C3 is V3. So the second property says the overall potential difference created by that battery or provided by the battery must be the same as V1 plus V2 plus V3. The potential difference across the capacitors connected in series add up. Now let's assume we can represent this relatively more complicated circuit by that circuit where you only have one capacitor. What is the capacitance of the single capacitor B so that these two circuits are equivalent. So that capacitance is known as the equivalent capacitance, as we saw for the parallel combination. The charges on this equivalent capacitor must also be plus Q and minus Q on the plates respectively. So for the equivalent circuit, we can quite simply write Q equals C equivalent times V. For the original circuit, since we know V is the same V as appears here, is the same as V1 plus V2 plus V3 using the second property, we see that since V is Q over CEQ, and V1 is quite simply Q over C1, V2 is Q over C2, and V3 is Q over C3, we can immediately figure out the expression for the equivalent capacitance here. It is quite simply the sum of the reciprocals. 1 over C1 plus 1 over C2 plus 1 over C3, like that. So generally, if you have n capacitors in series, the equivalent capacitance can be calculated using the following equation. So the inverse will simply add up 1 over C1 plus 1 over C2 plus 1 over C3 all the way plus 1 over Cn equals inverse of the equivalent capacitance. Problem 1. What is the capacitance of the single capacitor that is equivalent to the parallel combination of capacitors shown below? What is the total charge contained in the circuit configuration? So you have 4 capacitors, 3 microfarad, 6 microfarad, 12 microfarad, and 20 microfarad, and the potential difference of the battery is 18 volt. So let's calculate the equivalent capacitance of this circuit. So since the capacitors are connected in parallel, the equivalent capacitance of the circuit is just the normal linear sum of all the capacitance. So that is 3 microfarad plus 6 microfarad plus 12 microfarad plus 20 microfarad. Now microfarad, so it's 10 to the power minus 6 farad, which is 41 microfarad. So that's part A. Now part B, the total charge of the circuit configuration. So total charge is the sum of individual charges in this capacitor plus that capacitor plus that capacitor plus that capacitor. So the charge on 3 microfarad capacitor is the capacitance, which is 3 microfarad, so 3 times 10 to the power minus 6 times 18 volt. And you have to do the same for all the capacitors. So 6 times 10 to the power minus 6 times 18 plus 12 times 10 to the power minus 6 times 18 plus 20 times 10 to the power minus 6 times 18. I'm just using the fact that Q, for example, in the 3 microfarad capacitor is the capacitance of that capacitor times the potential difference across its plates, which is just 18 volts because they are connected in parallel. So the sum will become 7.38 times 10 to the power minus 4 coulomb. So that is the total charge contained in this network. Problem 2. Find an equivalent capacitance of capacitors in series shown below. What are the charge and voltage on each capacitor? So this is the equivalent circuit. So we know for capacitors in series, the inverse of the capacitance add up. So 1 over 6 microfarad plus 1 over 12 microfarad is 1 over the equivalent capacitance. And that's going to be 1 over 4. So that means the equivalent capacitance is a 4 microfarad. The charge on each capacitors must be the same as the charge on this equivalent capacitor. And that is quite simply C equivalent times 18, which is 72 microcoulomb. Now the voltage across the 6 microfarad, call it V6, is charge Q over 6 microfarad. And that's going to be, since Q is 72 microcoulomb, that's going to give you 12 volts. The potential difference across 12 microfarad capacitor, let's call it V12, is again Q over 12 times 10 to the power minus 6, which is 6 volts. You see, when you add this to that, you get the original 18 volts. Thank you for watching.